All right, so let us talk about the history of deep learning and let us talk a little bit about natural language processing. Um, First of all, we want to, in the beginning, neural networks were introduced as a metaphor of the human brain. You can see that metaphor graphically visualized here. You see a human brain that you can think of as consisting of different so-called neurons, which are connected to each other via weights. And if you have such a picture in mind, you can also see in this depiction of the human brain, well, you can also see the idea of neural networks that is deduced from such a imagination of the human brain, namely that you have different units that are connected, and maybe these units fire depending on whatever input comes into them. So this was the 1940s. This was the initial motivation for neural networks and perceptrons. Then in 1958, we already talked a little bit about that. There was Frank Rosenblatt that had, a paper or a book on that, which gave several properties of these perceptrons, what they are able to do. But then also later on, I think the same person criticized these perceptrons for their limitations, especially for the most popular case is that they cannot solve the XOR problem. That led to an awkward silence, AI winter, which also hit neural networks pretty heavily. People were basically not using them because they were considered to be very limited. Even though we had this deep winter which lasted for a long time, we did see some progress, some big milestones. For example, in the 70s and 80s, backpropagation was developed. This is an algorithm to train deep neural networks, which would work in principle but did not work in practice for a long time. And also, like in 1998, Jan LeCun, pictured here, had a convolutional neural network, which is a special type of neural network, recognize handwritten text, which was also a milestone. But basically, even though these individual milestones existed, neural networks were not the most popular technique, and other techniques instead had the upper hand. For example, support vector machines, you may have heard about that. They were like dominating the 1990s and also the 2000s. And then things started to slightly change around the middle of the 2000s. First, this can be attributed to individual successes again. For example, 2006, Geoffrey Hinton, which you see pictured here, had a paper where he showed that if you do pre-training, if you find good initial solutions for these neural networks, then they can work better. And I also had another paper on the restricted Boltzmann machines, which was also a kind of model which could do fancy things. But the second contribution why neural networks became popular again was that some people, including Geoffrey Hinton, thought that a better advertising strategy was necessary. So what they did is they changed the name from neural network, which was very unpopular at the time, to deep learning, which sounds much fancier. Um, this strategy also helped to increase the interest in neural networks and in then called deep learning. And then around the 2000s, we saw real breakthroughs. So, for example, 2012, Google Brain started, and also in 2012 there was AlexNet, which was a neural network, a kind of neural network, a deep neural network with many hidden layers that won ImageNet. So this is an image classification task where you have to label images according to the objects that are in there. And for the first time, a neural network could win this competition. And from then on, there was also big breakthroughs in natural language processing. So this is our core field in this course. So, for example, 2013 we had Thomas Mikolov and the so-called word-to-vec model, which many of you may already know. So this is a model that maps words into vectors, and it has very strong properties, and it gives good representations of words. And that was the breakthrough in NLP, and from then on, the whole field changed. So everybody was switching basically to neural networks, and nowadays almost nobody is using anything else than neural networks in our field. And like the highlight, so to speak, was just last year when Hinton, which you see here in the middle, Joshua Benjo from Canada, Jan Lecan also from Canada, Hinton is from Great Britain, when they won the Turing Award in computer science, which is the equivalent of the Nobel Prize. So this was really a major achievement and recognition of their work and of the impact that deep learning had already, and it is likely to have in the future. There's also a big German guy who is working in Switzerland. His name is Schmidhuber. He was the inventor of the LSTMs also back in the 1990s already. At the time, this was just theoretical breakthrough, but only much later did people find out that these models are actually quite useful, quite good, and they were the state-of-the-art models until just recently. But unfortunately, or however you want to call it, Schmidhuber did not get the Turing Award, even though several people say he would also have deserved that. So what can we say about the successes in image classification? So we already talked a little bit about AlexNet and how it won. So what was the situation before AlexNet? Here you see this ImageNet classification task. Again, the task here is there are pictures, and the computer has to decide which object is displayed in the picture. So the objects could be animals like cat, dog, elephant, or like a car or a human or something. And before neural networks, like in 2010, 2011, we had like traditional approaches, and they had like decent error rates, not too bad, not too good either, like between 20 and 30% error rate. Then in 2012 came AlexNet, and for the first time there was a neural network beating these traditional approaches, and from then on it went quite quickly. So like within a few years, the human accuracy level was achieved and then even surpassed. What do we have in natural language processing? Well, our major toolkit, so to speak, is machine translation. So this is translating from one language to another language. You certainly know the most popular such toolkit. This is Google Translate. The task is, as I said, translate between two languages. Could be English or Spanish, English French, English Chinese, Spanish English, French English, Chinese English. So there's also a matter of direction. Do you translate into English, from English? Of course, also other languages than English can be involved in machine translation. So here we see the quality measured in some ranking. What we had from the 1990s to 2000 to the 2010s was so-called phrase-based machine translation. That worked decently, and people spent a lot of money and a lot of effort and resources into that for 20 years, and it worked to some degree. It was still very limited. Machine translation output was still very limited. Then came neural networks starting from around, let's say, 2013, 14, until now, and in a few years they almost they are nowadays claimed to be close to the human performance level. Of course, then also it depends which humans do you take as a reference. Usually these are not professional translators which are taken as a reference, but maybe just ordinary bilingual people like for example me or you. But still, nowadays one can really say, and you certainly have tested that and checked that Google Translate works quite well for several language pairs. So under which conditions does deep learning work? So it's often claimed that data is important, size of the data is important for the performance, like for the accuracy scores, for example. And like here we have three different machine learning models. One is traditional machine learning, where we have, for example, linear models, etc. And these are claimed to work quite well when we have just little data. But then as we increase the data, the performance does not really increase. And what is claimed nowadays, the deeper your neural network, like here shallow neural network, that would be probably a perceptron. Or maybe it would be a multi-layer perceptron with just one hidden layer. Then medium would be more hidden layers, and deep would be very many hidden layers. So what is often claimed is the deeper your network, the more data does it need, but the better can also be your performance. When does it not work? As we've seen, like small data scenarios, that's often considered not to be ideal for neural networks. Then there's also the problem of the domain transfer. Like when your test data is very different from your training data. Imagine you have your neural network, you train it on news corpora, you want to apply them to Twitter. Then obviously that's a big change in distribution. Also, humans are affected by such changes. So if you would all the time read only Twitter, then you'd probably have problems understanding a more high-level conversation. So even humans, even humans have problems with domain transfer, domain change. But in particular, neural networks also have this, and all machine learning classifiers do. But there's some insight that maybe neural networks are a little bit more sensitive to such change of domain than other classifiers. And in particularly, they can be adversarially attacked. So what is that though? Like in 2014, 2015, Ian Goodfellow had like a seminal paper where he showed that if you have a neural network and it's performing some task. For example, it would do image classification and we have to classify that this is a pig. Then you can choose some small noise that is almost invisible to humans. So you have this small noise here. You just take a little bit of that noise and you add it to your original picture. You get a different picture which is basically identical for humans to the first picture, but your neural network would classify that totally differently, right? So why is that? So there are different speculations why that is, but one reason is probably that neural networks do not learn at least at the moment in the same ways that humans do. So they do not make the same representations of the data than humans do. So humans may use high-level logical inferences, while maybe neural networks do exploit very low-level statistical cues, and these low-level statistical cues could be that's sometimes called a dataset artifact. For example, if you want to classify whether a string is a person name or not, a neural network could find that whenever a opening bracket follows that name, then maybe this is a human person, because in newspaper text, for example, they often write the year of birth or the party affiliation in brackets, and the neural network could learn such very low level cues instead of making more deeper and richer semantic connections. Like if the verb has a special form, then the subject has to be animate, so it has to be a human. For example, eating a car can usually not eat unless you're using a metaphor. So humans might build such connections, and neural networks might not build such connections.